Hello, everybody. I'm happy to introduce Nico. He's a PhD student at UCSD working with Ranjit Jala. And today he'll be talking to us about refinement types for Rust. Thanks, Nico.
Okay, thank you for the introduction. Let me share my screen. Okay, can you guys see my screen?
Looks good.
Okay. So I hope everybody here have some interest in Rust. So Rust is this. I was checking like before when I joined the meeting that for a long time we've been presenting Rust as a new programming language, and I was checking at when are you gonna stop doing that. But anyhow, like Rust has been getting a lot of attention over the last years. This is like some data points like that people like to bring up. It has been selected as the most loved programming language for the past 7 years. It also got support into the Linux kernel. And also there's a lot of companies like big names putting money into Rust. So why is so much interest about Rust? This is what the website has to say about it. Allegedly, Rust allows you to write performant code, and which is also reliable. And I want to focus on that part, the reliability of Rust. And as you can see, it mentions in the web page that Rust has a strong and rich type system with ownership that allows you to eliminate many classes of bugs at compile time. For the most part, I think this is true. In reality, though, there are a lot of Rust code that can contain bugs. So this is a very simple example that I think is it shows a bigger trend in Rust that they trade memory safety by converting them into panics. So if you have this function print first that tries to print the first element of a vector, and then you call it with an empty vector, it will panic at runtime. And while panics are better than memory safety, still we would like to try to avoid them. So that's why we build Flux, right? So let me show you a quick demo of how Flux works. If you try to run the same program in Flux, it will complain saying that we cannot get the first element of the vector if we don't know if it is non-empty, and we can add annotations to the program. In this case, for example, saying that the vector must not be empty, and in that case, we get an error in the use side saying that we need to pass a non-empty vector. So if we fix that, then we can prove that the program doesn't have any panics. So the main premise of Flux and similar tools is that types can simplify verification. And so the theme of this talk is going to try to explain how we can use types to do verification. And the two main ingredients in Flux are refinement types and ownership types. And I'm going to explain throughout the talk the interaction between these two features that allow us to do verification in Rust. So let's start with refinement types. Quick recap. So the refinement types are a very novel idea. The typical way in which they're presented is like this. So you have a value name, a base type, and a refinement. And the idea is that you refine base types to those, you constrain base types to those that satisfy some property. This is something important, that typically those properties are drawn from an SMT decidable logic, such that type checking remains decidable and predictable. So as a quick example, we can have the type represented positive integers by constraining values of type int that are also greater than 0. So once we have types, we can use them to specify the behavior functions. So this is the type signature for a function that generates a list of integers within a range between low and high. And when we use our refinement types in an input position, then we can specify a precondition. In this case, that the second element has to be greater than the first. And when we use a refinement type in an output position, then we can specify postconditions. In this case, that all the elements on the list will be within the range of the inputs. So refinement types, I think it's safe to say that they're being fairly successful in the functional world. So two examples of successful uses of refinement types are liquid hassle and F-sharp, and they've been used to verify a variety of properties. But they haven't been too successful in the context of imperative programs. The reason why is because the very notion of a refinement becomes complicated, because in Haskell, for example, it is because values are immutable. It is very clear what does it mean to depend on that value, but what does it mean for a refinement to depend on some value if the value itself can change over time. So that's why we build Flux, and the insight here, as also many other verification tools for us, is that we can use the ownership system to try to extract from the extract a fragment that is pure, that we can safely depend on. So we do this in several steps. We start by indexing types with pure values. And then we use two of the Rust ownership mechanism, namely exclusive ownership and borrowed references, to track these refinements in the case where there are imperative updates. But then we realize that this is not enough, so we add a new ownership mechanism that records some references, and I'm going to go over this in detail now. So let's start by indexing types. So in Flux, an index types allows you to attach a refinement index or pure value to a type, and the meaning of this index depends on the value. So for example, I32 values can be indexed by the integer they're equal to. And in Flux, for example, we can give the expression, the Rust expression 2 + 3, the type I32 equals to 5. Similarly, we can index booleans by a pure boolean logical value that is equal to, and we can, for example, type the expression 3 less than 10 as the type boolean true. So it's not terribly interesting to talk about the specific value some types it is equal to. So we have some other features. So the first one is that in Flux, function signatures can be parameterized. So for example, this is a signature which is parametric on a local integer int, and it's stating that it's basically the signature for an isPos function that returns true if the input is positive. And you can think of these parametric refinements as ghost values. And in Flux, those are actually instantiated automatically. We don't typically use the explicit quantification with the for syntax, and we have like this more compact notation with the add notation. And also we have some more sugar. If you like your bindings on the left, we also allow this notation in which you have n colon and then the type. So the next features is existential types. So the reading for that is an existential type is a value that represents the values of type B indexed by V, such that some property holds about that value. An example of that is this type that represent positive integers, and we do that by indexing I32 by some value V, such that that value is greater than 0. So let me show you. I explain a bunch of features, so let me show you how this work. And for that, we're gonna try to verify an absolute value function. So what we are gonna try to prove is that this the result value is both greater than or equal to 0, and also is greater than to equal to the input element. So the way that we do that in Flux is by defining a refined signature. And so in this case, I'm parameterizing over the input x, and I can use an existential type at the output to say some property about the value. So for example, we can say that the value is greater than or equal to 0, and also greater than or equal to x. Sorry, if I had arithmetic overflow disabled, but if you think about it, if x is equal to the minimum possible I32, then the negation of that will overflow. Well, but we can easily put a precondition on that, saying that it has to be different than the minimum value. So any questions so far? I think this is a good point to ask for questions, because I'm gonna switch gears a little bit.
I had a question about the syntax. On the code you had for the return type. Why do you have to write v twice? You have v dot I32v. Which of these is the binding form? I guess is the part I'm confused about.
So in this form, you're existentially quantifying over v, and then indexing the type that v. So v is the binding.
Okay.
It is a bit redundant, so we have this shortcut form in which you can write.
Okay.
And I write it like this because the type here can be an arbitrary type. It doesn't have to be an index type.
I see.
Okay. Any other questions?
That's helpful. Thank you.
Okay, so let's continue. So far I've shown you like basically all the refinement mechanism we have in Flux, and now I'm gonna go and try to explain how the interaction with the ownership mechanism allows us to do verification. So let's start by doing some quick recap of Rust ownership mechanisms. So in Rust, every value has an owner, and the ownership can be transferred. So if we have we initialize some variable x to some vector, and then we assign that to y, then that value has been moved to y. And if we try to use x, then Rust will complain because it will say that the value has been moved by then. So I don't think many people think about it this way, but one way to think about ownership is that because we have exclusive ownership, we can do something that is called a strong update, which means that we can change the type of a variable at different positions in the program. So in this example, I have a variable x which starts with type vec I32, and then when I move it, I can strong update its type to be an uninitialized type. And then, for example, I can initialize it again, and it will have again vec I32. So this is something that like Rust ownership gives you out of the box. It's not too interesting in Rust because the only strong updates you can do is basically going from uninitialized to initialize and back. But as soon as we throw refinement, we can do something interesting because we can update the refinements we have on the type for some value. For example, we can start with some value that we know is equal to 0, and then as we mutate it, we update the refinement information we have about that type.
Yeah.
So questions so far? So let's go on. So the next mechanism that Rust has is borrowed references. Also, let me do a quick recap of what are references in Rust. So in Rust, there are two types of references: shared and immutable. A shared reference allows you to take to temporarily lend some value. This is the example that I took from the Rust book, in which you have a vec, and then you, for example, you can pass a reference to another function, in this case, calculate length. The idea is that inside calculate length, you will have immutable access to the value, and when you return from the function, then you didn't lose the ownership, and you can use it again. So the other one is mutable references that also give you temporary access, but they also give you mutable access. So I can call a function change, for example, and then mutate the vector by calling push. And when the function returns, then I recover back the ownership of the value. Something important to note is that a mutable reference has to preserve the type. So after I call change, for example, I know for sure that the vector is going to continue to be a vector. I cannot mutate it and put whatever arbitrary bytes in that location, right? So without going into too many details, the key property in Rust is that it only allows you to have either one mutable reference to a location or any number of shared references, and that's how they prevent many memory safety and databases issues. So I now want to focus on what do we get by combining these semantics for references with refinement types. So the first one is that when we have a shared reference and we put some refinement type inside that shared reference, then we can be sure that the value will satisfy the properties in that refinement type. So in this case, if I have a shared reference to positive integers, then I know for sure that the integers are going to be positive. And this is a consequence of the fact that when I have a shared reference, nobody can change the value, right? So the whatever property I have on that is going to remain true. Second, and a bit more interesting, you know, what happened when we put a refinement type behind a mutable reference. And as I was telling you, a mutable reference has to like preserve the type. So this way we can encode invariants using mutable references. In this example, if I have a mutable reference to a value that is I know to be positive, then I have to preserve that. And if I try to do any update on that type that doesn't may not satisfy the invariant, then Flux will complain saying that the assignment might be unsafe. So in this particular case, to fix the program, I will have to explicitly check that the update actually preserves the type. In this case, that it belongs being positive.
Can I ask a quick question on that one?
Yeah.
So is there a way to express that I want something to be true about the thing when it's passed to me, but I'm going to be updating it? Like if I wanted to take a reference to a slice to all positive numbers and I planned on negating all of them, guaranteeing that like when I gave a return control flow that they were all negative numbers, can I say something like that?
Yeah, that comes actually next. It's my next slide is that you exactly catch the problem. When these mutable reference, as I present them, you will get into trouble if you try to prove or know something about the value after you call the function. So in this case, if I start with a value c equal to 2 and then decrease it by calling the decker function, I would like to prove that the value is actually 1. But the semantics that you gave for mutable reference doesn't allow us to do that. It will only tell us that the value is still positive. So can we do better? And that's why we introduced the concept of a strong reference that actually allows you to do that. And we can give this stronger specification for decker in which we say that when the function returns, then the type of the location it is updated. There's an interesting interaction between strong references and mutable references, and I like this example to try to explain what's the difference. So whenever we create some allocate some value in the stack, for example, we have an x or y, you can think of it as having two locations, lx and ly, for which we have some type. In this case, I32 equals 10 and I32 equals 20. And then x and y are actually pointers to that location. So if I try to, whenever I know the exact location I'm pointing to, I can call these functions that take a strong reference. So in this example, I have two branches, and in each branch, when I take a mutable reference to the x or y, I know exactly where the reference is pointing to. So I can call the stronger version of decker and then learn that the value is actually one less than what it was at the beginning. But if I join them, because in each branch I'm taking a reference to x or y, when I join them, then I lose track of which exact location I'm pointing to. So I pack the reference into a mutable reference, and from that point on, I can no longer do the strong updates, but I can keep an invariant on that value.
Good.
Yep.
Are these comments syntax, or are do you have to have a Flux pack statement here for this to work?
No, this is all automatic.
I have another question. With non-strong mutable references in a function, are you allowed to locally store something that's invariant breaking as long as you store something that's correct by the time you return?
Yes and no. I mean, and we're currently working on implementing that. But the intuition is that during the duration of the lifetime of our reference, then you can break the invariant, and at the end you can resalvage it. But yeah, I'm currently working on implementing that.
Thanks.
So let me see a more realistic example. So far I've shown you very short snippets. So I'm gonna show you a refined IPA for vectors that I'm gonna refine or index by the length. So we can have, for example, a type of non-empty vectors by saying that the length is greater than 0. And also I want to point out that these vectors are polymorphic on the values they store, which will come in handy because I can instantiate that value for any refinement types. So for example, I can instantiate it for values that are positive, and that will tell me, allow me to keep an invariant over all the elements of the vector. So this is how the
How do you know the greater than makes sense for the elements of T? Or I guess, right? Well, actually, here isn't V a vector?
No, it is so the notation I have on top where I write refined by, I can pick an index, and in this particular case, I'm picking the index to be an integer. So the V in this case is an integer. And I'm just talking about the length of the vector.
Having a bit of a parsing, wasn't the value notation that you write type square brackets and then this refers to the thing of that type, or am I parsing that wrong?
So the notation at the bottom, I'm saying there's exists some V such that I have a vec index by that V, and then the V is greater than 0.
Yeah, but when vec is indexed by that V, doesn't that mean that vector is equal to V? Here it means that vector's length is equal to V.
Those square brackets V.
Index, they don't always mean a singleton type. And this is one example. When I index a vector by some V, then it only means that its length is equal to that V.
Okay, well, and my other question was, how do you know that greater than 0 makes sense for the elements of T?
I'm not saying something about the elements of T. I'm saying in this particular example, I'm saying that just the length is greater than 0. What I was trying to allude before that is that I can replace the T itself by a refinement type.
Is it possible to have two different kinds of refinement available for vectors so that you could do length or actual contents? Or can you only have one refined by for a type?
You could decide to refine about something else, for example, with a list of elements, and then you could keep track of the particular elements in the vector. Well, I have some more examples, so maybe some
Keep
stuff
going,
yeah. Yeah, we'll get to
I think that was positive.
in any case, this is the API we have for vectors. So the new length functions. So the new function will return you a vector stating that the length is 0. And when you're calling length on some vector, then you know that it will return a use size equal to the length of vector. The push and pop functions are a bit more interesting. They use strong references to specify that the length of the vector will be one more or one less than what it was at the beginning. And finally, the function index and index mut allow me to get access to a value in the vector, and they specify that the index has to be within bounds and give me back either a mutable reference or a shared reference to that t. Also, I'm going to stress now the function index mut is interesting, but because it's returning me a mutable reference to a t. That means that clients are allowed to mutate the value returned, right? But because mutable references has to maintain the invariance in t, that means that no matter how they mutate it, they will the vector will continue to contain elements of type t. Okay, so let me show you another demo now. So in this example, I have an implementation of the range function I mentioned at the beginning, where I create a vector of elements in some range. And this is what I was alluding to, is that the type inside the t inside the vector can be instantiated to any type. And in this case, I'm saying that all the values inside the vector has to satisfy this invariant, namely that they are within the range. And this is orthogonal to the fact that I'm also indexing the vector by its length. So let me show you a bit, try to demonstrate how this actually works in practice. So let's say we have two values low and high, and if I try to call range, Flux will complain because I don't know for sure whether high is greater than low. So we could add as a precondition of the function, or we could test it like explicitly, right? So if I do it, then Flux will let me call range. If I try to call pop on range, it will also complain because we don't know for certain whether the size of the vector is positive or not. But what we could do is try to iterate over the vector and try to pop from it. Oops. And in this case, because I know inside the loop that the vector is non-empty, then Flux will allow me to call pop. And moreover, I know about x. I know something about x by the return type of the function range. So, for example, I could assert that x is greater than 0. Greater than the lower bound. But I could not assert that it's strictly greater, but because the type of the function range doesn't specify that.
Nico?
Yeah.
Could you have made it so range had a return type that specified the length to be whatever it is, like high minus low plus or minus 1, whatever it is, and have it so that then because of the if, you could say if low is less than high plus, or if low plus some number is less than high, then you can pop it as many times as you are guaranteed to have elements?
Yes, so I could.
Okay, well, you don't need to do it live if that's gonna.
Yeah, but I'm just gonna show that I can actually specify that, and this is the way I will do it. I can say that the index of the vector is high minus low, and here I'm effectively proving that that indeed that's the size of the vector.
So once you have this, can you just say remove put a pop as long as the condition guarantees that there's one element?
Yeah.
Nice.
Yeah, exactly. Okay, so so far I think I showed you that we can indeed use types to do some verification. The question remains is that we can actually prove some interesting properties about programs. So we've done some evaluation of Flux. We mainly focus on two questions. Try to answer is one: can we first verify interesting properties using Flux? And the second one, which is our big claim, is that does Flux actually facilitate verifications compared with other tools? And so for the first question, we ported Wave to Flux. So Wave is a verified WebAssembly sandboxes runtime that was previously written in Rust and verified with Prusti, which is another Rust verification tool based on program logic. And Wave has it proves many interesting properties. It doesn't prove full functional correctness, but it proves some interesting properties. For example, first, that absence of panics in the sense that we are only accessing vectors and slices within bounds. It also proves that whenever we access in memory inside the sandbox, then those accesses are within the memory granted to the sandbox. And finally, and whenever we access some symbolic link, then that symbolic link is resolved to a path, a file path that is within the sandbox. So we were able to port all these properties to Flux without problems. To answer the other question, we wrote a bunch of small benchmarks, which consisted in loop-heavy vector manipulating algorithms like binary search and kind of smart stuff like that. And then we verified them both in Flux and Prusti. So what we found out is that one of the main advantages of using types is that because we are putting most of the information in types, then we can do automatic inference. So here you see a comparison of the examples that I was just showing, showing how it is in Flux. As you saw, we just write the specification for the range function, and then everything else follows. But if you try to prove that in a tool like Prusti, actually what's on the right is not Prusti, it's Creusot, which is a similar tool, then you have to automatically annotate all these loop invariants to convince the prover. And in Flux, you just get them for free. So we have some numbers for that. In this table, I'm showing the comparison we did between Prusti and Flux. So log is the number of lines of code. And we show the number of specs, which is how many lines it takes to specify the function, as in the function signature. The time of deprecation, and the invariance is the amount of lines used for loop invariants. As you can see, that line is completely gone from Flux because we are able to infer all the loop invariants. And in Prusti, they are non-trivial. Like heap sort uses is like a 24% of the code is used for just loop invariants. So the second thing to note is that we have very modest times. Quite proud of that. Our Flux is quite fast compared to Prusti. And we like to believe that one of the reasons because we can be so fast is because our by putting most of the information in types, then the queries we throw at the SMT solver are easier, and in particular they don't have quantifiers, which are known to be like hard for SMT solvers. Yeah, I think that's well. That's all I have. You can find the URL there, and if anyone has any questions, happy to answer them.
Nico, on the slide where you're just showing times, can you say more about what the measurement is for the time? Is that compile time? Is that time to invoke your tool?
It is a time both for the Rust type checker and the tool.
Okay, so roughly overall compile time with
Yes.
everything involved.
Yeah, with everything involved.
I was wondering, you don't have, is it that you don't have to express loop invariants, or is there no invariant that you could want to express that couldn't be inferred? what are the limitations or maybe not surprises? I haven't thought about, I was surprised you didn't show any manual specification of loop invariants, and then you mentioned here that you can infer all of them. Is that like, which surprises me. So what do we lose or?
Yeah, so the loop invariant invariant inference is based on fixed points. So if you're familiar with liquid Haskell, we are doing the same. And basically, we are able to infer loop invariants draw from a small set of predicate templates. So for example, we can infer like conjunctions of formulas built up from these templates. So these templates have to be provided by the user, but we also can infer them by looking at the signatures. Well, I guess a more specific option is that as long as the loop invariant is expressible using these templates, then we can infer it. And again, sometimes it'll be useful to annotate the loop invariants, but I don't think for expressiveness, more for sometimes because we're doing inference, the inference is can have unpredictable behavior, so it will help to annotate to help the tool.
So Flux does support explicitly written invariants, or
right now you'll have to rewrite the code in like extract the coding into helper functions where you can annotate the types. But yeah, we're looking into putting the annotations directly in the loops.
Oh, okay.
I have a quick question. Can you say a little bit about the language of properties? So for example, how are things like when you reason about the lengths of things, it is quite convenient to be able to write an upper bound that doesn't fit into the type, right? So, you know, because usually if you want to support all sizes, you know, you may want to, if you're talking about bytes, you may want to compare it to less than 256. Is this something you can write, or what are the types of the things in the properties? And how do they match to Rust?
The language of properties is basically whatever C3 supports. It can be an arbitrary logical expression that C3 supports.
But which theory? So in other words, how do you map the Rust types to Z3 types?
So that's why we have this notion of index types. There's where when you connect the logical value with the Rust type. So for example, I32s are indexed by an integer. And the semantics of that is that the interpretation of the Rust integer value is equal to the logical integer value.
So if I write 256, when I'm comparing U in date, is this an error or is this 0? What does it mean?
When you index that type with some value, it carries some invariance. So if you index I32, you know you have I32 indexed by n, then you know that n, it is within the range of that integer value.
But
that's something that your specification can exploit.
I mean, like if I write a constant, I say n less than 256, is that okay? Or maybe it's a type error.
I don't think I quite follow.
Well, I can index n is a uint8 thing, and I want to compare it to 256. So that's a thing I should be able to write, right?
If you index an integer type by some value that is outside of the range, then that is an inhabited type. You cannot construct such a value with that type.
Okay. So you have to fit everything in the types.
Yeah.
It's not integers that you're working with.
Well, it sounds like it is either unbounded, but like there is no U8 value that corresponds to the integer 256.
So I was wondering if U8 is being mapped to the theory of bits U8 or the theory of integers.
Yeah. So we
Implementation.
you could choose, and we have that option too. That if you wanna do like some bit operations, you can also choose to index the integers by a bit vector, and the bit vector will have the length. So you can choose whether to model integers as bit vectors or as an unbounded integer that happens to be within the range as an invariant of the type.
Can you choose to do both at different points of the same program?
You have to do some manual conversion, but yeah, I think explicitly cast it to one or two of the other representation.
All right.
And Nico, one of the things you indicated with the vector example is that the vector was indexed by its length. Can you talk more about, was len a REST function that was being used on the object itself, or is that something that's predefined?
But the vector itself, let me show you the API again. So the only thing you know about vectors is that they're indexed by some length. And then the connection of that length in the logic to the actual vectors comes from the API for vectors. Explicitly by when you call the length method on vectors, then you know that the return value will be equal to the length.
Okay, so on the previous slide, where you say refined by length is an integer, are you, how do you know length? Is that a REST function that's being called, or is that something you have to predetermine specifically for vector types?
Yeah, it's something that is in particular the API for vectors is not verified; it's assumed. So you can think of it as it is hard coded with that length, but there are ways in you could refine vector in. Okay, let me rephrase. You can slap a refined API on top of the vector, right? And in this particular case, we are choosing it to be refined by the length.
Okay.
I'm not sure if I understood that answer. I guess my question is like the name len here in the refined by annotation, is that significant? Like if I change this to say refined by foo::int, but left the rest of the API the same, would everything still work?
So we have some syntax. You can index the type for with more than one value. So in this case, we just have one value len, and we have a special syntax that if you only have one index, you can just use the value and it will represent the single index. But if you have more than one, there's a syntax in which you can like project that particular index.
Oh, okay. And so if you had sort of multiple refinements with different names, that's where this identifier here comes in?
Yes.
But so this identifier is not connected to, like Vec has a field named len and it has a method named len. Those are not actually connected to this len in any way.
No, not in any way.
Thanks.
That connection
Right.
comes from
At some point, you're going to have to.
That was my question too.
Yeah.
Yeah, that connection.
Yeah, at some point, you're
comes
going to
from
have to
the
basically.
methods.
I see.
You have a really flashy demo. Is that something that's easy for us to try out on our own computers? Or what's the current state of getting one of these and playing with it?
Yeah, and you have to compile everything from source. I think that the most complicated part is getting fixed point. So if you don't have like a Haskell setup, then you have to do that because you need to compile fixed point from source. But if you're interested in checking it out, we also have this playground. So that's it, and you can try it, Flux online. So the website is Flux Programming Systems.
Could you type in the repo?
The repo as well?
The phone.
And in this playground, we have a couple of examples that you can explore.
Okay, any other questions for Nico?
Yeah, me actually. Hi. So these strong references, they can only change the refinement itself, not the base type, right? Because
exactly.
I think about like you can't have a transmute that's somehow safe if you could verify which types are transformed into each other.
Yeah, exactly. You cannot change the base value because refinement types are still constrained by the Rust type checker. So every program needs to type check first by the Rust, and Rust wouldn't allow you to change the type. So if you to do that, it will require some support from the Rust compiler, which I think it may make sense to do, like safe transmute and stuff like that.
Okay, thanks.
I have another question. Can you use Flux inside unsafe blocks? Or will it not? Because a lot of the Rust checking is disabled in there. Is Flux also disabled?
Yes, I mean, nothing will prevent you from using Flux in an unsafe block. The question whether is can you say anything meaningful about the unsafe block? And I have two answers for that. One is that so you can use raw pointers, and the way it will basically work is that you can put any type under the raw pointer, but then it's up to you to actually satisfy that the pointer actually contains a value of that type. And the other answer is that we're working on refining safe abstractions over unsafe code in a way that they would let you, for example, have buffers of that are partially initialized, stuff like that. In the same fashion that Rust has like a safe wrappers over unsafe code, you can have a refined wrapper over unsafe code that will let you write like lower level code.
Okay, last call for questions for Nico. All right, thank you, Nico. This was great. We appreciate it. For everyone, this video will be posted to the Galwa website as well as distributed internally. So thanks again, Nico.
Okay, thank you.